everybody, I'm going to talk about radicals a little bit in this video. So radicals are definitely a very new topic that we have not encountered so far. So really it comes down to kind of what's happening when we're breaking bonds, right? So most of what we've been working with so far has been focused on a heterolytic bond cleavage. So if I have something like this where, maybe Y is a good leaving group, then I can end up forming these two ions where I have a positive charge on X, and I put my two electrons from my lone pair onto Y, making that negative. Okay, so then I've gotten two ions from that process. So when we're talking about radicals, though, we're really looking at a homolytic bond cleavage. So think about hetero being different, homo being the same. So homolytic means that we're going to have an even split of those electrons between X and Y. So instead of Y taking all those electrons, we're going to put one electron on X and one electron on Y and break the bond that way. So to do this, we have different arrows, and we'll talk more about the arrows in a second here. So we have these little fishhook arrows showing that we're going to be putting one electron on X, one electron on Y. So then that's going to give us two radical species. On X and Y, okay? So let's talk a little bit more about the arrows here. So the arrows are definitely a big change from what we've seen before. So what we've done in the past is we've had these double-headed arrows. Okay, they signify the movement of two electrons, so a pair of electrons each time. Okay, so now we're looking at radical arrows. These are often called fishhook arrows. And they just have a single head, well, a single point on the head, I guess. A lot of places you'll see them called fishhook arrows. And that is just showing the motion of one electron, okay? So in terms of, where the arrow starts and where the arrow ends, those are all still the same, right? So we're still looking at where this particular single electron start and where is it going. So that motion of arrow is still exactly the same. So radicals are also a little bit different in their geometry. Okay, so the geometry of a radical is pretty well explained if you think about kind of a little bit carbocation, a little bit carbanion. So let's just remind ourselves what the geometry of a carbocation looks like, because it's probably a little closer in that direction. Okay, so for a carbocation, we have something that's trigonal planar. And we have our empty p orbital. Okay, so that empty p orbital is just perpendicular to all of the CC bonds, and it's just going to be, flat, empty p orbital sticking straight up. So a radical is very similar to this. It definitely has more characteristics of the trigonal planar aspects than it does the kind of pyramidal that the carbanions have. Fix my angles here. That was really bad. Okay, so we still have a p orbital, but now instead of it being empty, we now have a single electron in it. Okay, and it's definitely going to have more of those trigonal planar properties. Okay, so when we think about a carbocation, we think about the fact that we can have some sort of nucleophile attack from the top or the bottom, because we essentially have a flat structure here, we're going to have a very similar situation here whenever we have a radical. We're going to think about that same process of some sort of reacting pair coming from the top or the bottom of that radical species. So we need to make sure that we're thinking about that when it comes time to think about, you know, stereochemistry and all of that. So when we think about the stability of radicals, they actually have a lot in common with carbocations as well. And actually, carbon radicals. Okay, so they're essentially going to follow the very same trends that carbocations do. And then the nice thing about radicals is that there are actually, quantitative methods that we can use to really kind of narrow down exactly what radical is going to be better using bond dissociation energies. Okay, so if we start off with the worst radical possible. Okay, this is the radical. And then down below it, I'm going to draw what it came from. And I'm going to highlight the bond that broke, okay? Because that's going to be what we use for bond dissociation energy. So for a BDE, okay, it's going to be measured in kilojoules per mole. And we're really looking at, you know, what is the relative energy if I break that bond and I end up with an H radical and a carbon radical, what kind of energy level am I looking at here? So the higher numbers are less stable, lower numbers are better, okay? So in this particular case, when I have my vinylic radical, yeah, okay, let's make sure I spelled that right. So the vinylic radical, that's going to have a bond dissociation energy of 464. Okay, it is quite high. And we'll kind of see as we go what the range looks like in this process. So, and this is pretty much as we expected, like a vinylic carbocation, we hate those two, right? Those are really bad carbocations. So if we go to a methyl radical, okay, so just a radical on a methyl, which would be something like this. If we just started from methane, for instance, that bond dissociation energy is 435. Okay, so a very big jump there between the vinylic and the methyl. And methyl carbocations, just like methyl radicals, they are not good. Okay, so then if we move on to a primary radical, okay, which came from something like that. That's going to be 410. Okay, a secondary is 397. We go to tertiary. That gets us to 381. And then just like carbocations, resonance is a big contributing factor to stability. So if I have an allylic radical, okay, and I'm looking at breaking one of those CH bonds that's in the allylic position, that takes me down to 364. And a benzylic radical is going to be even better. And that's going to be at 356 kilojoules per mole. Okay. You absolutely do not need to memorize these numbers. I'm giving you the numbers and they're in your book because they are handy to use when you're thinking about radical reactions. But if you are feeling pretty comfortable with the trends of a carbocation stability, just make sure that you kind of map the radical ones on into that because they're going to be very similar in terms of their trend and progressions. So do not need to memorize the numbers. I'm just giving them to you so you can kind of see what the differences are like, right? So we have almost 100 kilojoules per mole difference, which is a huge difference when we're talking about the stability of a vinylic radical versus a benzylic radical. And that should really kind of help guide you as you're drawing reaction intermediates to make sure that you're not drawing or preparing a radical that's going to be just too high of an energy to actually prepare. So, and keep in mind when you're looking at radicals, all of these carbons here are neutral, okay? So make sure that we're keeping that in mind as this has, you know, 2 hydrogens on it. So if I'm counting up for formal charge, I essentially have 1, 2, 3, 4 electrons that carbon in the middle owns, and carbon has 4 valence electrons. So radicals are neutrally charged, but they are certainly not stable because they still don't have a full octet, okay? So carbon radicals, actually let's put this in orange. They are very reactive, okay? They don't have a charge. But that lack of a full octet definitely has some impact. All right, so let's look at an example of how to kind of draw some arrows here. We're just going to start with just a resonance question, just so that as you're practicing with these arrows, you can kind of start getting some of that pattern recognition building up. So we're going to work with a benzylic radical. And we're just going to do resonance to see where we can go with it, okay? So the thing you want to keep in mind here is the closest pattern that we had from when we learned resonance to begin with is going to be this pattern where you have a lone pair next to a pi bond. That's going to be most of what you need to do for resonance structures with radicals. So if we remember what we had here, we had 2 electrons moving to form a new pi bond, and then that pi bond formed a new lone pair. Okay, so we want to remember this. So now our new pattern here for radicals it's going to have some similarities, but it's going to have more arrows with it, right? Because we're only using 1 electron at a time, but we still have to do something that looks very similar. So this electron, this radical, wants to form a pi bond, but we need to have 2 electrons to form a pi bond. So we're going to take one of those electrons from our neighboring pi bond, and these are going to meet in the middle to form a new pi bond here. But I still have 1 electron from the pi bond that I have not dealt with. That is going to become our new radical, okay? So it's very similar to this pattern. We just have an extra arrow because we're moving each electron individually, okay? So whenever we have 2 heads meeting together, we're going to form a bond. If I've got a head just landing on an atom, that's going to be where my new radical sits. So let's use that pattern on this example here. So first thing, we have a radical next to a pi bond. So we're going to first move our radical to form a new pi bond. Bring in one of the electrons from the pi bond currently, and then that other pi electron is going to end up on this carbon, okay? One thing that might help when you're getting started on this is to kind of do the ABC method and think about like, okay, if this is A, and this is B, and this is C, then I can kind of keep track of where things are going and make sure that I think the most common part that students run into is difficulty of where to put that final radical. And if you kind of number things out so that you have A, B, and C all connected, and then A, B, and C all connected, you're not going to do anything funky like try to put a radical over here or something like that. Okay, so let's go ahead and draw out that resonance structure. So now I've got a new pi bond here. I've got my radical there. And I have everything else is still untouched and unchanged. Okay, so now I have a couple options. I can either go A, B, C, or A, B, C, right? So both of those are pi bonds. I can go either direction. I'm going to go towards the oxygen first here. Okay, so I'm going to go use that radical to make part of a pi bond, get the other part of the pi bond from that other pi, from the CO pi bond, and then put my final radical up on my oxygen. So now I've got a pi bond between A and B. My oxygen, which is C, previously had 2 lone pairs on it. Now it has a radical on it as well. And everything else is unchanged. Okay, so I also could have gone the other direction. So if I go A, B, C, we're going to have pi bond forming between A and B, radical ending up on C. Okay, so now I've got another situation where I've got A, B, C. So now form another pi bond between A and B. Radical ends up on C. And then I have a radical over there. Okay, so it's pretty much very similar to resonance that we've done previously. You're just kind of doing extra arrows because you've got kind of electrons meeting each other to form bonds. So if we're only moving one at a time, but we're still needing to make bonds, we have to make sure that we're having enough electrons to actually form those bonds. So we will practice all of this and talk more about radicals next week. So have a good weekend, and I'll see you all later.